Welcome back. Till long day after, today I will discuss uniform continuity. But today I will discuss uniform continuity not only in real number. Today I will discuss what is the uniform continuity in metric space. This is the goal of this lecture. Let's see what is the difference of uniform continuity in real number and metric space. Okay, let's start our original goal of this lecture. At first say what is the uniform continuity in real number. Then I will discuss what is the uniform continuity in metric space. At first recall what is the continuity in real number. We all of us know a non-empty set. Consider the non-empty set A, which is subset of R. Consider one point small a belongs to A and consider a mapping F from A to R, which is continuous at the point A, means x goes to A. That implies fx goes to f of A. This is actually the meaning of continuity. We all of us know. Continuous at the point A means x goes to A, and if x goes to A, then fx goes to image of this point fx goes to f of A. But uniform continuity means the point which is close to each other, that imply their image also close to each other. This is actually defines between continuity and uniform continuity. Here x goes to one specific point, but here all are arbitrary point in the set. Okay, this is actually difference in between continuity and uniform continuity. And in metric space, from this picture we all of us know what is the definition of uniform continuity in real number. First, consider a function f from x dx to y dy. This function is uniform continuous if given epsilon greater than 0, there exists delta greater than 0 such that distance between the point x1 x2 on the set x less than delta imply distance between the point f of x1 f of x2 on the set y less than epsilon, and this is true for all x1 x2 belongs to x. In real number, distance on the set x between the point x1 x2 less than delta means absolute value of x1 minus x2 less than delta, and distance between the image f of x1 and f of x2 means absolute value of f of x1 minus f of x2 less than epsilon. This is the definition. This is the picture in real number. Okay, well, I hope my all viewers have understood what is the uniform continuity in metric space. Definition of continuity in metric space, that imply f is continuous at a point x means for all x belongs to the metric space x, and for all epsilon greater than 0 there exists delta greater than 0 such that for all y belongs to x, distance between y and x less than delta imply distance between f of y and f of x less than epsilon. That means here this delta depends on not only epsilon, this delta depends on also point. If I consider another point, let's consider x1, x2, x3, x3. For different point, delta would be different. This is actual difference between uniform continuity and continuity. Here delta depends on not only epsilon, this is depends on points also. We all of us know the difference between the continuity and uniform continuity. In continuity, delta may depends on a specific point in x belongs to S for a continuous function. But for uniform continuity, delta depends independent on x. Uniform continuity always defined on a set and continuity defined at a point or on a set. And here I have considered a subset of x, and f is uniformly continuous on the set A. If A is finite set and given f is continuous on the set A, when A is finite, that imply always f is uniformly continuous on the set A. Why? Because f is continuous on a set A means for each point in this set, since A contains finite number of points, if A contains m number of points, consider for each point, for continuity there exists delta 1, delta 2 up to delta m. Now, if we consider minimum of this delta 1, delta 2, delta m is delta, then these delta work for all points on this set A. So, when A contains finite number of points, then we can tell f is uniform continuous on this set A. Okay? Well. But when the set is infinite set, then function may be continuous, but it may not be uniformly continuous. On discrete metric space, every function is uniformly continuous. For this, consider delta equal to half. If delta equal to half, then d of xy less than half and d of xy less than half. This is true in discrete metric space when x equal to y. We all of us know this. And since x equal to y, so that implies d of fx fy equal to 0. It's obviously less than epsilon. So every function in discrete metric space continuous, also uniformly continuous. I hope my all viewers have understood this concept easily. This is very easy concept. Okay? Well. Now consider one function g from R to R such that g of x equal to x square, and this is true for all x belongs to R. For this, let epsilon greater than 0, then mod gx minus mod gy equal to modulus of x square minus y square, and this imply mod of x minus y times mod of x plus y, and let mod of x minus y less than delta, then this imply mod of x minus y times x plus y less than epsilon. Since mod of x minus y less than delta, this is delta times mod of x plus y less than epsilon, and we can write absolute value of x plus y equal to absolute value of y minus x plus 2x, which is equal to 2 mod x plus delta. Therefore, as they put here, then this implies delta times 2 mod x plus delta, which is less than epsilon. And If delta is less than mod x, then whole part imply this is less than, delta is less than 3 mod x, and if mod x greater than 0, therefore delta was greater than 0 and less than minimum of mod x comma 3 over mod x, delta works in this interval, and here delta depends on point. So the function is not uniformly continuous on real number. If we consider the closed interval a equal to 0, 1, then this function is obviously uniformly continuous, because absolute value of gx minus gy equal to absolute value of x square minus y square, and this is equal to x minus 1 y times x plus y, which is less than equal to absolute mod x minus y times mod x plus y, and mod x plus y less than equal to mod x plus mod y. And since a belongs to 0, 1, therefore this mod x less than equal to 1 and this mod y less than equal to, therefore this is 2 times mod x minus y, which is less than epsilon. Therefore delta equal to epsilon over 2 for this delta. This function fx equal to x square on this interval is uniformly continuous. Okay? I hope my all viewers have understood this concept easily. Okay? Oh well. All of us know continuity in sequentially. Today I will discuss uniform continuity in sequentially. For this, consider one function which is mapping from xd to y row, which is uniformly continuous on the set x. If for any two sequence xn yn in x which is satisfying d of xn yn tends to 0, imply row of f of xn f of yn tends to 0. This is the uniform continuity in sequentially. This is another definition of uniform continuity by sequence. Okay? Well, this is some example. In few minutes ago, I have seen fx equal to x square not uniformly continuous on whole real number. If you see the graph, this is the graph of y equal to x square. Consider 2 points here and distance between these 2 points. If we consider points which goes to infinity, and consider same distance between this point, but these distance would be different. Notice this distance and this distance will prove this function is not uniform continuous on whole real number by sequential. This function is not uniformly continuous when the point goes to infinity. So consider two sequence such type x1 equal to n and x2 equal to n plus 1 over n and n greater than equal to 0, and consider epsilon equal to 2 and delta greater than 0. Then f of x2 minus f of x1 would be n square plus 2 plus 1 over n square minus n square. Now cancel this part. This value would be 2 plus 1 over n square. Notice here mod x1 minus x2 equal to 1 over n, which is less than delta, but f of x1 minus f of x2 greater than epsilon. So this function is not uniformly continuous, we can tell by sequentially. Okay? Have you understood? Oh well. Now I will see new function fx equal to 1 over x. When x belongs to closed a infinity, in this domain, obviously the function is uniformly continuous. Because notice the picture. If we consider 2 points, here, then the distance would be here such type. But when the point would be close to 0, then if we consider same distance but their distance would be same points in same distance but their distance from graph would be different. So the function is uniformly continuous on the closed interval a infinity, but the function is not uniformly continuous on 0 infinity. Let's see the proof. Absolute value of fx minus f of y, which is equal to 1 over x minus 1 over y, and this is equal to absolute value of y minus x over xy. And since here x belongs to closed infinity, therefore this is less than equal to absolute value of y minus x over s square. And this is y minus x obviously less than delta, that means delta over s square, which is less than epsilon. Therefore delta less than s square epsilon. Here delta depends on only epsilon because s square here just as a constant number. So the function is uniformly continuous on the closed interval a infinity. Function is not uniformly continuous on the interval open interval 0 infinity. For this I will prove this by sequentially. For this consider two sequence near to 0. I will prove this function is not uniformly continuous near to 0. So consider two sequence which near to 0, x1 equal to 1 over n and x2 equal to 1 over 2n, and consider epsilon equal to 1 and delta greater than 0. Then absolute value of x1 minus x2 would be 1 over 2n, and by Archimedean property we can tell 1 over 2n always less than delta, but absolute value of f of x1 minus f of x2, this value would be 2n minus n, this value would be n, which is greater than equal to 1. So this function is not uniformly continuous on the open interval 0 infinity, but this function is uniformly continuous on the interval closed a open infinity. I hope my all viewers have understood. I will prove uniform continuity of any function by sequentially. How I will consider the sequence? Here I have considered these two sequence because function is not uniformly continuous on the interval open interval 0 infinity. Now let's see some properties of uniform continuity. First property, if a function which is defined from closed interval ab to r, which is a continuous function, and we all of us know continuity always does not imply uniform continuity, but if the domain is closed and bounded, then continuity always imply uniform continuity on this domain. And at first I will prove this. For this, assume the proof of this, assume f is not uniform continuous. And definition of uniform continuous, we all of us know. For each epsilon, there exists one delta. That means, since I have assumed f is not uniform continuous on the domain AB, therefore there exists one epsilon for which no delta works. And this definition is such type, there exists epsilon greater than 0 such that Given any delta greater than 0, there exists two sequence x delta and y delta which belongs to this domain AB such that absolute value of x delta minus y delta less than epsilon. These imply f of x delta minus f of y delta greater than equal to epsilon. Okay? For this, choose delta equal to 1 over n. And since I have chosen delta equal to 1 over n, that means there exists two sequence. Xn belongs to closed interval AB and Yn belongs to closed interval AB such that absolute value of xn minus yn less than 1 over n. But since I have considered it, if is not uniform continuous, that means absolute value of f of xn minus f of yn greater than equal to epsilon. Okay? And since AB is closed and bounded interval, therefore, by Bolzano-Weierstrass theorem, we can tell there exists a convergent subsequence of xn, call it xnk, such that xnk converges to x0, and since xnk belongs to the closed interval AB, since the function is continuous, so xnk goes to x0. That implies obviously f of xnk goes to f of x0 by the result of continuity. Okay, and since absolute value of xn minus yn less than 1 over n, therefore absolute value of xnk minus ynk less than 1 over nk, and by this inequality we can tell xnk minus 1 over nk less than ynk less than xnk plus 1 over nk, and since xnk goes to x0, therefore this part goes to x0 and this part goes to x0. Therefore, by Sandwich theorem we can tell ynk also goes to x0. By Sandwich theorem we can tell this. Okay? And by continuity, since the function is continuous, so that implies f of ynk goes to f of x0. Therefore, f of xnk minus f of ynk goes to f of x0 minus f of x0, and this value is equal to 0. These conditions break our assumption, because for our assumption f is not uniform continuous on the closed interval AB. This is wrong assumption. Since I have assumed f is not uniformly continuous, so this condition has hold. This is contradict our assumption. So the domain is closed and bounded, then continuity always implies uniform continuity. In continuity, we all of us know if xd and yd prime are metric space and f be a function which is mapping from x to y, then f is continuous at a point if and only if every sequence which converges to x that imply f of xn converges to f of x. But in continuity, suppose f be a mapping which map from domain to R is a continuous function, and let xn be a Cauchy sequence, then that imply is fxn is Cauchy sequence? Is it true or not? Continuity, this is not true. Cauchy sequence does not map to Cauchy sequence. As for example, consider fx equal to 1 over x square, where x lies between open interval 0 infinity. Consider one sequence xn equal to 1 over n, which is Cauchy sequence. Then f of xn equal to n square. This is not Cauchy sequence, because we all of us know Cauchy sequence means this sequence always bounded. But here f of xn equal to n square, this sequence not bounded. So this sequence cannot be Cauchy sequence. Therefore, in continuity, Cauchy sequence mapped to Cauchy sequence, this is not true. Now consider f which mapping from domain of f to R which be uniformly continuous. Then if a function be uniformly continuous, then xn is a Cauchy sequence that always imply f of xn is Cauchy sequence. And this proof is very easy proof. We have to prove f of xn is a Cauchy sequence. Therefore, given epsilon greater than 0, there exists capital N such that for all mn greater than equal to capital N, absolute value of f of xm minus f of xn less than epsilon. We have to prove this, and given the function f be uniformly continuous. So, using uniform continuity of the function f, for epsilon greater than 0, there exists delta greater than 0 such that absolute value of x minus y less than delta imply absolute value of fx minus f of y less than epsilon. Then, since xn be a Cauchy sequence given, therefore there exists capital M such that absolute value of xm minus xn less than epsilon, and this is true for all mn greater than equal to capital M. By the property of uniform continuity that imply obviously f of xm minus f of yn less than epsilon, this is true for all mn greater than equal to capital M. Therefore, this imply the sequence f of xn is also Cauchy sequence. Since this function is not uniformly continuous on the intervals open interval 0 infinity, so we cannot tell f of xn is also uniform continuous. Hope my all viewers have understood all properties of uniform continuity. This topic is very important for higher study. Okay? See you soon. Stay safe and stay positive always. In my next video, I will discuss this type of topic elaborately. Okay? Thank you so much for watching my video.